Good morning students. Today we are going to discuss one of the process synchronization primitive called as semaphores. So before going to discuss about the semaphores, we have to know what is meant by a process synchronization and what is meant by a critical section and what is meant by a race condition. So the main aim of the semaphore is to avoid to solve the critical section problems and to avoid the race condition in process synchronization. Actually in nowadays all the process the execution we are using multi-programming. So in multi-programming more than one process is executing at a time. That means more number of processes are executing concurrently. When the more number of processes are executing concurrently, so when those processes are sharing the variable, so when we are accessing the shared variable concurrently, so all the processes are want to access or manipulate the data, shared data, then data inconsistency will occur. To avoid that, so we are going to use some primitives for process synchronization. So process synchronization is nothing but the communication between the processes. So here we are having two types of process. One is a cooperative process and non-cooperative process. In cooperative process, the execution of the one process may affected by the execution of the other process. So in cooperative process, if they want to access the shared data, so we have to concentrate on the synchronization, process synchronization, or the communication between the process. So here in this session we are mainly going to discuss about the one of the process synchronization primitive, that is semaphores. So we are having so many primitives like locks or mutual exclusive locks. So locks, we are having different types of locks, that is test and set locks and compare and swap locks, mutual exclusive locks, like that. So those are all the hardware based solutions. So here the semaphore is a software based solution. So the hardware based solutions may, so the programmer developers are unable to understand. That's why, so we are going to the one of the most used process synchronization primitive called as semaphore. So in this session we are going to discuss about the what is meant by a semaphore and what are the different types of semaphores and what are the critical section problems and how can we address that critical section problems by using semaphores. So here the scientist Edgar Dijkstra he developed the semaphore. So here the semaphore is a technique to manage concurrent process by using integer value. Here semaphore is nothing but an integer value, so which is known as a semaphore. So semaphore is an integer value. Semaphore is an synchronization tool that provides more sophisticated ways than the mutex locks for process synchronize their activities. For process synchronization we are using these semaphores. Here the semaphore is nothing but an integer variable, that is the semaphore is going to shared by the different process. So semaphore S is an integer variable which is used in mutual exclusive manner used by concurrent cooperative process in order to achieve synchronization. So in order to reduce the data inconsistency on executing concurrently, on executing of the concurrent process, so we are going to use semaphores. A semaphore is an integer variable shared among the multiple process. The main aim of using semaphore is the process synchronization and access control for a common resource in a concurrent environment. To use a shared variable in a concurrent environment, we are going to use these semaphores for process synchronization. So here if we want to interact with the semaphores, we are going to use two functions. The first one is the same weight and next one is the same signal. Generally the same weight is called as P and same signal we are calling as denoted by V. In most of the textbooks or in most of the references, so in some case they are using same weight and in somewhere they are using P and in somewhere they are for signal operation they are using V. So how this P and V, what is this, how this P and V came and what is this P and V denotes. So here the scientist who discovered the semaphore is Edgar Dijkstra. He is an Dutch scientist. So here the P denotes proben, Dutch word proben, and the V denotes the Dutch word verozen. Here proben means to test and verozen means to increment. So why they used P for the same weight and V for the same signal? So we can know by seeing the definition of these functions. So here the same weight function. So same weight function here, if we want to interact with the shared variable, that is a semaphore, so we are mainly going to use two functions, that is the same weight and same signal or same post. So here the same weight function, the definition of the same weight includes, here what we are going to use same weight, this is the definition of the function. So we are using one variable, that is S. S is nothing but the semaphore. Here what we are doing, here we are testing the condition that while S is less than or equal to 0, that means we are checking the some condition whether the semaphore value is less than or equal to 0 or not. If less than or equal to 0, that is busy waiting. So here the semicolon behind semicolon after the while statement, that indicates that whenever this condition is true, the loop is executing in this while statement only, that is busy waiting. Whenever the condition will becomes false, then the next statement is going to execute, that is here the semicolon denotes. So here first we have to check the condition, after that whether the semaphore value is less than or equal to 0. If the semaphore value is less than or equal to 0, the process is in the busy waiting state. So if the value is not greater than 0, so here this statement is going to execute. Here what is going to happen, the semaphore value is going to decrement. That means, so here first of all what we have to know is, in a same weight, so the semaphore value is going to decrement. So after that next one is the same post. Same post, in this simply we are incrementing the semaphore value. Okay, so same post, so here we are simply incrementing the semaphore value. So where we have to use this same weight and same post. So actually we are going to use this semaphores to solve the critical section problem. So what is the syntax of the critical section? So the syntax of the critical section is do. So here entry section, do, here entry section, after that critical section, exit section, and this is the reminder section, while condition. So here in entry section what we are going to do, in entry section, so here we have, when we are going to use this semaphores or any process synchronization, so we have to maintain the mutual exclusion. That means at any given instant only one process is allowed to enter the critical section, because here to avoid the race condition, that means what is meant by a race condition? So the race condition means if more than one process is accessing or manipulating the shared variable, the value of the outcome, is mainly depends upon the order of the execution of the process. Okay, so to avoid that race condition, so we are going to use this critical section. So here the critical section is mainly contains the code or data which is shared by the more process, that is shared data or files or tables are going to store in the critical section, are going to store in the critical section. So if any process wants to enter into the critical section, first we have to check some conditions whether the critical section is available or not. So here we are going to check that condition. After that, if the lock is available or the critical section is available, the process will enter into the critical section. After completion of the execution of the critical section, it comes to the exit section. So after that, the remainder section is going to execute. That is, so we have to maintain the mutual exclusion. So mutual exclusion means at any given instant only one process is able to enter into the critical section or access the shared variable, or in terms of resources, at any given instant one process is able to access the resource. Okay, so here in entry section we have to check the condition. If available, the process is going to enter. So here the same weight, in same weight what we are going to do, we are checking condition. After that we are simply decrementing the value. So here the entry section consists of the same weight operation. After that the critical section. After that in exit section what we have to do, we have to use the same post. Same post means here the semaphore value is simply we are incrementing the semaphore value. That means this same post or same signal, semaphore signal will denote the critical section, that is the process. Suppose we are having P1 and P2. So process P1 first execute this same weight operation, so it enters into the critical section. After completion, the process P1 we have to execute same post operation. Okay, that process P1 has to execute same post. That means that indicates that the process P1 completes its execution of the critical section. So any other process can access the critical section or can enter into the critical section. So here in a same weight what we are doing, we are testing and we are decrementing. So here the proben. So proben means to test. The meaning of this Dutch word means to test. So verozen, the meaning of this Dutch word is to increment. So here we are simply incrementing and here we are testing some condition and we are decrementing. So that's why in some references same weight is denoted by P and same signal is denoted by V. Okay, these are the two main functions. If you want to interact with the semaphores, these are the two main functions, that is the same weight and same post. So what are the different types of semaphores? So here we are mainly having two types of semaphores. The first one is the binary semaphore and next second one is the counting semaphore. As we are all know, binary semaphore means the value is either 0 or 1, two values only. The value is either 0 or 1. The counting semaphore means it is the integer value can range over an unrestricted domain. Okay, so let us discuss how this binary semaphore is going to how we can use this binary semaphore by using this same weight and same signal operations. See here, same weight initially. So this semaphore is an integer value with some initial value. So here first we are taking the S value is 1. Okay, that means the critical section is available. That means no process is executing its critical section. So here first what we have to do, here we have to check the condition. That means S value is less than or equal to 0. Here S is 1. That means S value is not less than or equal to 0. So here the S value is going to decrement. Here S value will become 0. Okay, so while executing semaphore S, the same weight operation, so here we are taking two scenarios, process P1 and P2. So first the process P1 is executed same wait operation. So initially the semaphore value S value is 1. So after this the S value will become 0. So in second scenario, the process P2 wants to execute its critical section, so it execute the same wait operation. So here the semaphore value is 0. So when the process P2 wants to execute this same wait, so here we have to check this condition, that means S is less than or equal to 0 or not. Here the S value is less than or equal to 0. So the process P2 has to wait until the S value will become greater than 0. Here the process P2 has to wait. So whenever after completion of the execution of this critical section, the process P1 executes same post. So here what is going to happen? Here the S value is going to increment. Initially the S value is 0. So after incrementing, the S value will become 1. That means when here the process P2 is waiting in this same wait in this while loop. So whenever the S value will become greater than 0, that means the process P2 is get access to the critical section. Here S value is 1. So S value is 1. So here again S value is going to decrement, S value will become 0. That means the process P2 is going to execute its critical section. After completion of the critical section, the process P2 has to execute same post or same signal operation. That means any other process is able to access the critical section. Like that, the binary semaphore is going to work on this same wait and same post operations. So next one is the counting semaphores. So counting semaphores is the same. Actually here the counting semaphores is mainly used in case of, suppose if we are having the many instances of a same resource or many instances of the resources, we are going to use counting semaphores. So the counting semaphore value is first initialized to how many number of instances are available in the system. Okay, so the number the initial value of the counting semaphore is the number of resources or instances of the resources available in the system. For each and every resource we are going to use a separate semaphore. So the counting semaphore value will denote the how many number of instances are present for that particular resource. So the execution of this counting semaphore is same as the binary semaphore, but here in binary semaphores the initial value is 1. So in counting semaphores the initial value is equal to the number of instances of the particular resource. So next one is the main disadvantage of this same wait and same wait operation or semaphore. The main disadvantage of the semaphore is busy waiting. See here we have to check the condition. While the semaphore value is less than or equal to 0, the process has to wait, busy waiting. So for the process has to wait for the critical section to implement to execute the critical section. So here to avoid this busy waiting, see here whenever the semaphore value is S is equal to 0 or another process wants to execute, so the S value will become -1. So 0, so the process has to wait. So by this busy wait, the process may starve. Okay, it has to wait more time. So that may to avoid that, to avoid this busy waiting, we are simply we are modifying the function of the that is modifying the same wait and same signal operation. Simply we are adding two another functions, that is block and wake up. So here to avoid busy waiting, we are slightly modifying the definition of the same wait and same post operations. So we are including two functions, that is block and wake up. So here we are taking a semaphore for each semaphore there is an associated waiting queue. That means we are sending the process which are waiting on that semaphore into an waiting queue. Then the state of the process will change to the ready to the waiting state. Okay, the change of the state of the process is changed to waiting state. So here each semaphore is associated with a waiting queue. So here the semaphore is having a value, that is a type integer, and next one is the pointer. That pointer is used to point to the next record in the list. So this is the simple definition of the semaphore. So semaphore is having the value and the list. Star list means that is a pointer to the next record in the list. So this is the slight modification of the same weight and same signal operations with to avoid the busy waiting. So here what we are going to see, first S value is initialized to 1. So S is equal to 1. So initially what we are going to do, S value minus minus, that means S value is going to decrement, S is equal to 0. So here S will become 0. Here we are checking the condition that S value is less than 0. So here no, S value is equal to 0, not less than 0. So this if statement is not going to execute, and simply the same the process executes its same weight operation, the S value is 0. So if another process, that is this is a process P1, if process P2 wants to execute its critical section, so it is executing same weight operation on semaphore S. So here the S value is 0. So initially what is going to happen, the S value is going to increment, that means S value will becomes minus 1. So here we are checking the condition whether S value is less than 0. So yes, so add this process to the S list, that means we have to add this process to the waiting list. Okay, so we are adding this process to the waiting list. So that means the state of the process changed to waiting. So so here what we are calling the block operation. So the main aim of the block operation is it simply add this process to the waiting list. So after execution, so after completion of the execution of the critical section, the process P1 executes same signal operation. So in same signal what is going to happen, S value plus plus. So here what is S value, minus 1. So here S value plus plus means S value will become 0. So if the S value is less than or equal to 0, yes, the condition satisfied, remove a process P from the list and we have to call the wake up operation on process. Okay, so we have to remove the process from the waiting list, and for that we have to call the wake up operation. That means the process P2 is ready to execute. Okay, then that means the state of the process changed to ready state. Okay, after completion of the same signal operation of the P1 process. Okay, so like that the operation, the same weight and same signal operations are going to execute to avoid the busy waiting. So here how the main problems when the processes are executing the concurrent manner, the main problems will occur is the deadlock and the starvation. So what is meant by a deadlock? Deadlock means two or more processes are waiting, indefinite waiting. Deadlock means indefinite waiting. If the two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting process. Okay, that means we are taking two processes P1 and P2. So the process P1 is waiting for an event to occur by the process P2. That is, P1 is one of the waiting process and P2 is another waiting process. The P1 is waiting for the event occurred by the process P2 and P2 is waiting for an event occurred by the process P1. In that situation, the two process has to wait indefinitely. So no, the requirement of the no any one of the process is not satisfied, the resources are not available. So these two processes will go into the deadlock state. So let us see by using some simple example. So here we are using two process P0 and P1. See the execution of the statements. Process P0 is executing same wait on semaphore S. Okay, here they are using two semaphores S and Q. So the process P0 executing same wait operation on semaphore S. After that it is executing same wait operation on semaphore Q. After that after executing so many statements, it is going to execute same signal operation on S and same signal operation on Q. So meanwhile the process P1 is executing same wait operation on semaphore Q, and after that same wait operation on semaphore S. After executing so many instructions, the process P1 is going to execute same signal on Q and same signal on S. See here, the first process P0 executing same wait on semaphore S. Here P1 is executing same wait on semaphore Q. So here the process P0 executing same wait on semaphore Q. Okay, so here the process P1 is already executing the same wait operation on Q. That means the process P1 is executing in the critical section. So here the process P0 is executing the critical section on semaphore S. So if the process P0 wants to execute this same wait on Q, the process P1 must execute the same signal on Q. Okay, if the process P1 wants to execute this same wait on S, the process P0 has to execute same signal on S. So when the process P0 execute the same signal on S, the process P1 is able to execute same wait. So whenever the process P1 wants to execute same wait on S, the process P0 has to execute the same signal on S. So the process P0 is waiting for an operation for an event occurred by the process P1, and process P1 is waiting for an event occurred by the process P0. So these two processes are in the deadlock state. Whenever this process P0 completes the same signal on S, then only the process P1 has to complete same wait. So when this process P0 completes this same signal after completing this same wait on Q, right? So it has to wait indefinitely and it has to wait indefinitely. When this same wait on S will complete, after complete when this process P1 executes this same signal on Q after completing this same wait on S. Okay, so we are calling this as a deadlock state. So the process P0 and P1 are in the deadlock state. To avoid this that is process P0 and P1 are in a indefinitely waiting state. So here starvation means indefinite blocking. Okay, so we have to, so by using this semaphores, so we have to achieve the process synchronization in an effective manner. So we have to mainly concentrate on this deadlock and the starvation also. Okay, in next session we are going to discuss about this, what are the classical problems of synchronization and how to address these classical problems of synchronization by using semaphores. Thank you.